I'm going to continue along the theme that we explored earlier. So by now, hopefully, you're convinced that SageMaker is awesome, right? Yeah. It is pretty cool, right? It is pretty cool. It's, you know, it's still very new. It just came out a month and a half ago. So yeah, you know, it's not obviously not perfect, and you could make it even easier to use, etc. But you know, I find it's really a step in the right direction. I mean, if you've done machine learning the normal way, a lot of those steps that look super obvious in SageMaker, well, they could take a few weeks of work, right? So, having said that, maybe you don't want to use SageMaker, right? Maybe you want to keep working with MXNet, or maybe you want to keep working with another framework. And maybe you want to use EC2 instances and the deep learning EMI, because you know that's the way your stack is set up for now. And you know, I understand that not everybody's going to jump into SageMaker in an instant. Maybe you want to experiment with it before you move it into production. So in this talk, you know, I'm going to pretend that SageMaker doesn't exist. All right. Actually, it's a talk I did at reInvent. So probably the very same day SageMaker was announced. And this is focusing on I would like to say it's pretty much everything I know put into slides when it comes to MXNet. It's pretty close to that, actually. I don't think I forgot anything major. So it's all the techniques and the tips that you should use to make your training process more efficient, right? And there are two angles to this. There is obviously the model performance, the one we all obsess on. Oh, what should be my learning rate? What should be my optimization algo? How many epochs should I run? You know, the stuff that keeps you awake at night. But I find that there's a second topic, which I'll call infrastructure performance, that is at least as important, right? Because if your training jobs run too slowly, then you're not going to be able to iterate fast enough, right? You're going to wait for hours and days for training to complete. And so that means you're not going to get many chances to update the model and tweak the model. So I think these two things go hand in hand. So you need the infrastructure to run at full speed with maximum performance during training. And that gives you the ability to tweak and tweak and tweak and tweak the machine learning and deep learning part, right? Okay, makes sense? So some of the stuff I'm going to say is really advanced. So some of the slides will make you go, huh? Right? They still make me go, huh? Sometimes, so fine. So don't worry, it's not supposed to be, it's very dense. It's not supposed to be understood in one go. And the last thing I want to say is it is really level 666. It is very very advanced, and some of that stuff also makes sense for other frameworks. So although I am talking about MXNet, a lot of the tips here are also applied to TensorFlow or other frameworks. Okay, so if you're not using MXNet, don't leave the room. Listen anyway. You probably will pick some good tips for the other libraries. And then at the end of the session, hopefully my image classification notebook will be complete and I can show it to you, right? Hopefully. So let's start with optimizing infrastructure, okay? So here's, again, the name of the game is I want the training jobs to run as fast as possible because that saves me money, right? Because you're paying by the second, sure, but, right? You want to save some seconds, huh? And save some money. And the faster they run, the more you get to the more you get to iterate and try something else, if that wasn't too efficient anyway. So the first problem here, and somebody asked a question earlier about sharing the data set, right? And actually, it's a very good question. How do you efficiently deploy a large data set to multiple instances? The data set I've worked with today, they're really tiny, right? They're megabytes, so no issue at all. ImageNet, I'm going to show you ImageNet hopefully afterwards. It's 150 gigs, right? So that's a lot, and it's a million files and more. So it's not easy to move around, right? So the first technique that you should implement is to pack the data set into a record IO file. Okay, and TensorFlow has that same notion. They're called TF record files. If you remember, when I downloaded my data set on that image classification notebook, I just downloaded a .rec file, and that's exactly what this is. So it's one file storing the images and the labels. Okay, and it's one big file, but it's only one file. So it's much easier to move one very large file than to move millions of small files. Okay, plus, if you want to do distributed training, the structure of the record IO files help instances split the work among them because they're records, so it's easier to say, you take this chunk, and I take this chunk, and you take this chunk. Okay, so it's super easy to use. There's a tool in MXNet called im2rec to pack those files. It doesn't take long, and you do it once, but you train many times, right? So take the time to pack your data set. You will thank me. Okay, it's a really good way. And again, you can do the same thing in TensorFlow. So once that you have that, you have your huge data set into, I forgot to say, I love image classification examples, so I am always talking about images. So you have an image record IO file, and which works best for images, and you have a generic record IO file that could be anything, right? So it's not just for images. Important precision here. So now, once you have your data set, where do you copy it, right? Well, you could say, well, S3 makes sense, maybe, but not only S3. So one pretty fun technique that I have is I copy that data set on a dedicated EBS volume. So I create an EBS volume, I mount it on an instance, and I dump the .rec files in there. Okay? And I take a snapshot. Because once you've done that, even if the data set is, gigabytes, you can super quickly create a volume from the snapshot and attach it to the instance. So there's no copying involved, right? So, because if you put it in S3, you have to copy it or access it from S3, which is maybe slower. So if you put it in a volume, snapshot it, right? That takes maybe a while, but then creating a volume from a snapshot takes seconds. And then you attach it to the instance you want to train on, and you're done, right? And if you need 10 volumes because you want to do distributed training, then you can create 10 volumes from the same snapshot, attach them to their instances, and you're done. So in seconds, right, and that's easy to script automate. So in seconds, you could make very, very large data sets available to instances just by using that, okay? The only downside is you're paying for the cost of the EBS volume and the snapshots, okay? Which is maybe a little more than S3, but in any case, it's super fast. It's the fastest way to deploy, actually. So if you don't want to do that, of course, you can store them in S3. You have an S3 connector in MXNet, provided that you built MXNet with the use S3 flag, right? Just try it, and if it says, sorry, you need to use the use S3 flag, okay, then you need to rebuild. And you can access files directly from S3 using the typical syntax. So very cool, S3, unlimited storage, high durability. Problem maybe, lower performance. You will get lower throughput from S3 than EBS. Okay, so for very large trainings, maybe that's a problem. And maybe it's more of a theoretical problem. I had never actually faced it, but you could have a hotspot if you have 100 instances learning from the same .rec file hosted in the same servers. Maybe there's a hotspot, but I don't know. It's more of me being paranoid than a real problem. Another option would be to use EFS. Okay, the point here would be an EFS volume can be shared across instances, right? It's NFS, so you could mount the same volume on multiple instances and share the data set. Okay, so it's very simple for distributed training, no copying, no nothing. The problem is EFS is more expensive than EBS and S3. Okay, so long term, if you have a large data set, that's probably not the right way, right? Maybe you need S3 for long-term storage and EFS for training intense periods of time and then kill EFS volume. And EFS performance modes are, needs to be investigated. You have two modes. You have a general purpose mode, which is fine, and you have a max I/O performance mode that delivers more throughput, but usually at the cost of added latency. So that could be a problem for training. You could stall your instances because they are waiting for EFS to answer. Okay. Again, I never really faced it, but I'm guessing this could happen, right? Okay, so that's it for storage. So 3 different options: S3, EBS, EFS. You make up your own mind. Okay, and all of that stuff obviously is applies to any deep learning library. Now the second thing is, okay, so you've got storage taken care of. Now, how do you keep the GPUs running at full speed? Okay, these are really hungry beasts, right? And that's a problem, because the faster they get, the faster everything else needs to get. So you should be able to feed them at the right speed. Otherwise, they work and they stop, and they work and they stop, and you never get the full throughput. And that happens a lot, okay? So how do you know what the right speed should be? Well, if you've been running trainings before, you have some benchmarks. You should look at the logs. You could say, well, I know this should train at 500 images per second or blah, blah, blah. So you should, that's a training benchmark, a training indicator that you could track. Maybe you could look at numbers and benchmarks reported by others. People tend to share their training data, etc. So you should look at what kind of performance people get, and do you get something close enough or not, okay? And then, of course, you should look at how the NVIDIA GPUs are running. Okay, so there's a tool called NVIDIA SMI, and it's going to give you the list of GPUs and their power consumption and how busy they are, right? And you should look at that, and the rule here is simple. They should all be at 100% and stable at 100%, right? If you see, 50, 100, 20, 70, well, that's not good, because it means they're stalling and they're not being fed fast enough. Okay, so there is a throughput issue somewhere. Could be storage, could be something else. All right? So one parameter is batch size. Okay, so the batch size is how do we slice the data set and how big those slices are when we push them through the network for training. Okay, so this is an important parameter. Usually people will agree that a larger batch size is more efficient, okay, because you push more data at the GPU, so you keep them really busy, right? You can keep more cores on the GPU busy. But a smaller batch size usually gets you to better results because you take smaller steps through the data set, so it's usually better. So not too big, not too small, right? Not very scientific, but you need to find something in between. So here are a couple of suggestions. If you have a small data set with a few classes like MNIST, right? 50, 60K samples, 10 classes, or CIFAR, 50K samples, 10 classes, then a good rule of thumb is 32 multiplied by the number of GPUs you're training on. Okay, that's a good starting point. And you don't want to go too big, right? Because if you go with really big batch sizes, imagine you have 50K samples, right? If you have 10, 24, let's say 1,000 as the batch size, you will go through the data set in 50 steps, right? 50 times 1,000. So that means for one epoch, you only get 50 steps to learn and to run backpropagation in the deep learning network, right? So that's not enough, probably. So if you use, let's say, 4,000, maybe that's 12 steps. So for each epoch, you only get to adjust the weights 12 times, and probably that's not enough, okay? So don't go too high, otherwise your training process will be screwed up. Okay, so you need to be reasonable. On the other hand, if you have a large data set like ImageNet, millions of images, 1,000 classes, then you should use the large possible batch size. And how do you find that? Well, it's pretty funny. You start at this, and you increase it until MXNet fails because the GPUs run out of memory. Okay, so you just push it. You see memory usage in that NVIDIA SMI tool. So just push it to the max. Okay. If I have to make a snarky comment, right? It's the end of the day. I'm allowed to do that. You cannot use this technique with TensorFlow because TensorFlow allocates the full GPU memory, even if it doesn't need it. So if you have 10 gigs on the GPU, it's going to allocate the 10 gigs. So when you look, it says, oh, I have allocated 10 gigs. I'm running at best performance. No, obviously not. Okay, the memory usage you will see for MXNet is the real memory usage. So if you change the batch size, you will actually see this going up. I did write a blog post a time ago on this. Got really funny reactions, but hey, I was right, so never mind. So MXNet, is pretty conservative, so it tells you exactly how much memory it uses. So just push it, increase it, right? And until you get MXNet to yell at you saying, no, you will get an ugly error message saying GPU out of memory or something. And okay, well, then you went too far. Okay, so that's fine. We're pushing as much data as we can into the GPUs, okay? And using NVIDIA SMI, we should see that the memory is fully used. And yet, maybe GPU usage is not at 100%. So we're filling up the GPUs, but they still stall, right? So it's like, hey, here's a big bunch. They go through it, and then they stop. Oh, here's another big bunch, and then they go through it, and they stop. Because you don't feed them fast enough, right? They're really hungry. So remember, a deep learning job, of course, it's running on the GPU, right? The training part. But there's a Python process running next to that. Okay, it could be the notebook, it could be your own Python process, the script that you're running. Okay, the training script does not run on the GPU; it runs on the CPU. A lot of people forget that. Okay, so is that process keeping up? Right, the iterator. Remember that we saw that morning the object that feeds the data to the GPU. Is it running fast enough? Because if not, you're stalling. So you can use all the usual techniques. You could use stop to check the load, to count how many threads are running, and generally get a sense of, is this machine busy enough? Right? If you see the GPU stalling, and if your CPU load is like 5%, that's it. The CPU is not working hard enough to feed the GPUs. Okay? So you need to make sure that Python process is working hard to read the data from storage and push it through the GPUs. And another good reason to use those record IO files is that you can specify the number of threads that are working on the IO. Okay, so you could say, give me more threads, read more stuff in parallel and push it to the GPU all the time. So just make sure you max out that Python process, make it work as hard as possible, because if it's too relaxed, then it's going to starve the GPUs, and your training times are going to explode literally, right? So if the Python process is really maxed, and you have the max number of decoding threads here, then maybe you have an I/O problem, right? Maybe it's the I/O layer that is actually slow. And again, top would tell you that. If you look at the idle time for the Python process, it would tell you, yeah, I'm doing what I can, but I keep waiting for I/O. So we need faster I/O. So top and I/O stat maybe would help you figure it out. I've never run into a problem with EBS. EBS was always fast enough, but okay, who knows? So maybe you could look at local storage. You could use some instant storage. That's faster. Or why not use a RAM disk, the good old technique from the 80s with Windows 3.0. That works super fast, right? These instances, they have hundreds of gigabytes of RAM. So you could create a RAM disk, put the data set in there, and the I/O problem is solved, right? And if something happens to the instance, no big deal, you have the storage, the EBS storage backing you up. So I tend to use RAM disk, which is a bit of a silly technique, but it kind of solves the I/O problem, right? Think about that. Distributed training. So I told you this morning, MXNet scales very well. It scales almost linearly up to 256 GPUs. So how do you get to 256 GPUs? Well, you use 16 instances with 16 GPUs and you throw them at the same data set, right? It's an expensive demo, don't try it. Again, I'm not paying my bills. It's very easy to set up. It's really, really easy to set up. There's a good demo here, right? And again, record I/O are pretty much mandatory. It's pretty much mandatory here because I said, again, it's going to help instances split the data set easily. Okay, so I'm not going through the full setup, but you can really set it up in 10 minutes. There is nothing weird about that. Okay, that's all great, and more power to GPUs. But what if you don't have a GPU, or what if you don't have the budget for GPUs? You saw the prices for GPU instances this morning. And what if you want to work on your own machine? Well, you have some libraries that help speed up machine learning and deep learning on CPUs. Okay, so you have two options. One, which I'll show you, which I will demo. It's called the Intel MKL. So it's a kernel, it's a math library optimized for Broadwell and especially Skylake architectures. So there is a compilation option for it. Okay, so it's very easy to see if MXNet has been built in with this. When you start it, if it doesn't say MKL blah 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 with a version number, then you don't have it. Okay. There is an open source alternative called NNPack. Anyone knows that one? Yeah. I like this one. It's not as fast as MKL, but I love it because it works with Raspberry Pis, right? It does support the ARM7 architecture. Okay. And yeah, it's a cool project. You can also use performance libraries like JPEG Turbo and Gemalloc and Google First Tools to speed up various parts of the process. Image manipulation and memory allocation. These are usually not built in, but yeah, feel free to try that. Okay. The biggest benefit will come from probably using MKL. Okay. So MKL, you can find it on GitHub, and basically it's optimized implementations for all these operations that we've been talking about today. So convolution, activation, pooling, plus all the matrix algebra, right? Optimized versions for Intel chips. Okay, so it makes a big difference, as you will see. So if you want to run training and prediction on C5 instances, right? Like I said this morning, it's the cost-effective way to do it. Make sure you use MKL. You will see why in a few minutes. Of course, you could use Spot instances. So I told you this morning it was very hard to grab P3 instances in Spot right now. It's easier to grab P2s, right? Here's an example. This is from September, the end of September, so it's not that old. And that's a US West 2, so it's the Oregon region. And I could find some P2 16XL, so 16 NVIDIA GPUs at 89% discount, right? So that's pretty good, right? That's a good deal. Okay, P3 is more difficult right now. I don't know if I mentioned that example already, but I don't remember. But Clemson University ran a few months ago a very large natural language processing job on 1.1 million virtual CPUs. So that means 500,050, 55K, no, scratch that, 550K actual physical cores. Okay, so 500,000 plus physical cores on AWS. Okay, so people ask me about the scale of AWS. Okay, so one customer can do this, right? For a few hours on spot at a very low price. I don't know the exact budget for this, but if they were clever, you know, it's probably a silly low number for that kind of processing power. 500,000 cores, you know, it's like one of those top 10 supercomputers, right? That's the kind of thing the kind of performance you get for, I don't know, I don't want to say any number because I don't know the number. I can only guess, but a ridiculously small amount of money, right? So here's a hint on the scale of AWS. Okay, of course, it's pretty easy to select which GPUs you want a job to run. So, you know, if you have 16 GPUs on a machine and you have 16 developers in the team, well, again, it's a silly trick, but just say, hey, you're number 1 and you're number 2 and you're number 3. And right, you could use one instance and share the GPUs across developers. People don't think about this, right? But, you know, I think it's, you know, it works for me, right? Okay, so let's look at C5 and MKL, right? Quick demo here. Okay, so this is, what is this? Yeah. Okay, so that's a C5 instance, okay? So Skylake architecture, no GPUs. And I think this one is the non-MKL version. So it's just vanilla MXNet, okay, that I built. So we have a cool little script here called benchmark score. And let's run that. Yeah. And so what it does is it builds a number of network architectures and runs prediction on random images. Okay. And of course, you see how many images per second you get to. So it starts with AlexNet, which is it's an older CNN now. It was very popular a few years ago. So it builds completely random data and pushes it through the network. Here, the goal is really to see how many images per second can we do, right? Okay, so, and we do with batch size from 1 to 32, right? So predicting one single image or predicting 32 images, right? Which gives you a sense of, can we do, let's say, a real-time video analysis with this, right? Can we do 24 images per second, right? Okay. Okay, and then it tries the inception network. Okay, so let it run. And now let's use the same instance type, but this one, oops, this one is built as MKL built in. So if I was clever, I'd do something like this. Well, what do you think? So as you can see, it says MKL blah, blah, blah. So that's how you know you have MKL running. So let's look at inception, for example. When predicting one image at a time, we can do 4.8 images per second without MKL. We can do, man, that's a crazy number. We can do 86 images per second. So you see the speed up that you get, right? And you can just use that thing for free. Just make sure you build MXNet with this. Okay, and then, right, same thing here. 2 images per second on Inception v3, which is the real number. 33 images. So you could go video, right? You could stream a video to this and still be able to make 24 images per second. Right? So depending on the networks, you get different results. But, right, I rest my case. You have to use MXNet. You have to use MKL when you use MXNet.
Sorry, if you compile MXNet for the right processor architecture in the first place, you
Yeah, but MXNet is not, it's C++ code, right?
Yes.
So you can optimize it. You can use GCC and use all the optimization flags that you want, right? You will not get to that same level here because MKL, it's assembly code written by Intel, tweaked for their instruction set. It's the processor maker writing the code.
Should make much of a difference.
Well, it does. It does. Well, it does. I'm sorry. Right? And it's not just the instruction, it's the way you run the computation, the way you do matrix multiplication, the way you do convolution, etc., right? Here you use, I would say, portable C++ code, and here you use highly optimized assembly code, and it makes a huge difference. You can trust Intel to know their chips here, as you can see.
Yeah, I know very bit about it. Like if you run the first code through the Intel compiler, that compiler is really good, right? Should actually get very close to
Yeah.
that.
Yep. I don't want to use the Intel compiler. I want to use my compiler. I see your point, but right? To me, that's the faster route. And here, okay, let's compare this. Okay, so let me put that one here. Oh, that's weird. Can I still scroll? Okay. And this one is, okay, this one is a P3 16XL, so that's like the top one. Lucky I could grab one. So eight Tesla chips, okay? So super powerful. And let's run the same script. I'm going to run it on one GPU. What I want to show you here is the difference in performance between one Volta chip and one C5 instance with MKL. See how far away they are or not. Okay, so we can see here we are running on GPU 0. So which one is this one? Okay, it's AlexNet. Oh, okay, yeah. Okay, so AlexNet, huge difference, but I would say no one uses it, that one anymore. Let's look at Inception. Where is that one number here? Okay, okay, so Inception on the C5 was 86 images per second if I do one image at a time. On a GPU, it's 111. So sure, it's higher, but it's only 50% better, right? Given the cost, the relative costs, I would say you should use C5, right? Now, if you if you want to do, let's say, video prediction, you have batches of images, 32 by 32 showing up, then sure, the difference is much bigger. Because on the GPU, you have so many cores that you can run that batch in one go, right? The Volta chip, it has 5,000 cores or so. So yeah, much more than the C5. But in most cases, and let's maybe look at another one, Inception v3, 71 when you do image per image, 33 when you do image per image. So okay, it's a 2-to-1 ratio for performance, but it's much more than 2-to-1 on price, especially if you do spot, where it's much easier to grab C5s than to grab P3s. Okay, so if you want to do prediction for, let's say, a mobile app, people take pictures and they take a picture and they want to run a prediction. Okay, it's an image by image thing. As you can see, inference with C5 is much more economical. If you want to process high resolution, real-time video feeds, yeah, depending on the network architecture, maybe the GPU works better, maybe depends, right? But sure, as you increase the batch size, the thousands of cores of the GPU, they just destroy everything else, okay? But a lot of tasks are really classifying one image at a time. Okay, so here's a good example here. Okay?
How would it compare to a decent gaming laptop, not laptop, a gaming computer, consumer computer?
Well, you have some consumer versions of those chips. I mean, the Titan, did you see that one? It was a good gift for Christmas. The Titan NVIDIA, yeah, you saw that one. That's $3,000. I didn't get one, but I have a Mac anyway. So yeah, you could as long as you have a GPU, a recent NVIDIA GPU, you can do that stuff, right? But the problem is, I would say if you need to build a development machine, right, and you want to be autonomous, then okay, go and buy a reasonably sized GPU and use deep learning with it. But if you need to scale this for production, right, again, instances are pretty expensive. If you want to do your own infrastructure, hosting that stuff in a data center is going to cost a lot because you pay for electricity and cooling, right? And GPUs, they tend to need a lot of that. So, right, I would say for development machines or test environments, why not? Why not go and buy something and build it? But for production, just use instances, and that's what I would do, right? But again, if you have a mobile app and you have millions of users uploading one photo at a time for prediction, you cannot beat a fleet of C5 Spot instances. Right? Because you're going to be able to, even from a web serving point of view, right? You want to scale out. So same old. One super powerful GPU instance or two super powerful GPU instance, they will be less scalable from a request point of view than 50 C5s, right? But if you need to do, again, high resolution video analysis, probably you need GPUs, okay? But try it. Okay. Let's talk about model performance. So model performance means I want to build the best model possible, the most accurate model possible. So one cool technique to improve your data set, let's go in order, is to use data augmentation. Maybe you've heard about that one. So data augmentation means you take your existing data set and you build more samples. So you flip the pictures, you resize them, you crop them, you distort them, you change the colors, right? If you flip a cat picture horizontally, it's still a cat, right? So depending on the settings, you could build maybe 16 or more different images from a single sample. And that will help your data set get bigger, and that will help your data set grow more general, okay? So MXNet and Keras, they have those data augmentation tools, and you should definitely use them. Okay, they're really nice. Especially when you want to do fine tuning. If you have just a few thousand images, right? Data augmentation is a good way to move from a few thousand to a few tens of thousands, and maybe help build a more robust model. So then, you need to look at initialization. So initialization means you need to start all your weights, or all the weights for the neural network. They need to have an initial value, right? And usually something tells me, well, we can just start with 0, right? Well, the problem is if you have symmetric and identical values in the network, chances are that some networks will have actually the exact same training, right? Because when you adjust the weights, you're going to adjust all the weights in the same direction or with the same increments or decrements, and that's not what you want. So you need to start with random values, right? To break that symmetrical effect. So they shouldn't be too large or too small, right? Which is something that you see a lot in deep learning, right? So come on, that's not helpful. Okay, so the consensus is, and I'm sure you could do a PhD thesis, and you could do your whole career on this, probably. So I don't have that time. Is to use the Xavier technique. That's actually the name of the guy who invented it. For CNNs, it's quite popular. I see that in all samples, in all code samples from all leading researchers. So, it's got to be good. I trust those guys. And for everything else, just random values between 0 and 1. Just pick a normal distribution, and you will have those initializers, okay? So I wouldn't play smart, and I wouldn't play smart and use anything else. I don't know any better. This seems to work fine. Don't spend too long on initialization. Just use those techniques and spend your time on something else, such as the learning rate, which is everybody's nightmare. Again, it should be too small, it should be too large. If it's too small, you will never learn. If it's too large, you will never converge, right? So you will never find the minimum for the loss function, for the error function, and you will bounce back and forth. So that's not good. What I know is that it's actually a good technique to try to keep a learning rate, a large, quote unquote, learning rate for a long time, because you will get closer to the minimum faster, right? If you take large steps for a while, then chances are, you will converge fast and get closer to the minimum for the loss function, and then reduce it, right? Imagine you're walking in Stockholm, you're walking from here to some location near the train station, right? The train station's that way, I guess. So you can walk pretty fast for probably more than that, 15 minutes. I don't know. I took a taxi. Right? So you can walk that direction pretty fast, and then you can say, okay, I'm getting near, so now I'm going to slow down and actually start looking at the signs, right? So that's the intuition here. So here are some techniques, and again, you could use that with any kind of framework. So you could keep it simple and stick with a fixed learning rate. Say, okay, I'm going to use 0.01, and if it trains for 3 days, fine. I'm not in a rush. But if you're running this on AWS, you still are paying for by the second. So thank you, but we'd like you to save money. Another technique is to use steps. So you could say, I'm going to run with this learning rate for 20 epochs, or 1,000 batches, or you could take different steps, and then I'm going to reduce it. Okay, so like I said, walk fast and then slow down, and then slow down, and then slow down. And the closer you get to the destination, the closer you get to the destination, the slower you learn to explore and make sure you really find that local minimum. Or, and that's obviously my favorite option because I'm lazy, is to use an optimization algorithm that figures it out for me, right? If you've run some deep learning tutorials, probably you used an optimization algorithm that is called SGD, right? Stochastic gradient descent, and you need to have a learning rate. And then it's like, oh my God, that's too small, or oh my God, that's too... And we'll see in a couple of slides, you have algos that actually ignore this and they figure it out. They adapt automatically the learning rate to the situation. That's fantastic, right? No nightmares. So if you want to do steps, this is how you would do it in MXNet, and you can do it similarly in other libraries. So you could say, well, every time you have run 100 batches, reduce the learning rate by 0.9. Well, multiply the learning rate by 0.9, decrease it by 10%. Okay. Or you could say, well, these are my epoch steps. Okay, so each time I reach one of those epoch numbers, just multiply the learning rate by 0.9. Okay, but what I don't really like with this is that, yeah, I see that gentleman, because you would have to know what to expect, right? It's like, why 100 and not 150? It's like, yeah, it's like guesstimates, right? So I don't really like that way of doing things, but you can see that. If you have prior knowledge of your training, if you've been training this thing for a month and you looked at the graphs for the accuracy, etc., you say, okay, up until that point I can learn very, very fast, and then I need to slow down and learn slower to improve, etc. So maybe as a late optimization stage for a very mature model, a very mature training process, that's okay, because you know what your training is going to look like. But in the beginning, I don't think that works, right? Because you tend to assume that 100, epoch 100 is important. And, so either you know or you're assuming. And if you're assuming, it's not optimal, okay? So that brings me to optimizers. So we have many, like other libraries. And the only thing I know for sure is that none of them works all the time, right? I would love to tell you, use that one all the time and you'll get the best results. Well, that's not like that. Here's a silly example. That MNIST data set that you saw earlier this morning, that training that I ran, okay, with the LeNet convolutional neural network. I tried it with a bunch of optimization algorithms, okay? So here's the time per epoch, and here's the validation accuracy I get after 20 epochs. So you can see a lot of, pretty large differences, right? So, for example, that one, is super slow, right? Super slow. So training is literally 6 times slower than vanilla SGD. And yet, it gets to a lower accuracy. So, duh, right? Science doesn't always work, okay? And, well, that one is only twice slower, but, I get a much better result than the SGD, right? So, that brings me to the difficult subject of, well, you gotta try them all, right? It's like Pokemon, right? You gotta catch them all. You know Pokemon, right? I've got kids. Don't worry, I don't play Pokemon. But it's the same thing. You have to try them all. One of them for that specific network and that specific data set and that specific set of parameters is going to work best. Okay? And if you were here for the SageMaker talk, I said in preview we were working on hyperparameter optimization, and that's because we want to solve that problem for you. You could experiment with this for days and weeks and tweak and try to find it. So what if SageMaker could tell you, well, try this. Try this, kid. It's going to work, right? Try to give you automatically the best settings possible. You could tweak for this. Try it. It takes a while. But until you do that, you should really try them all, okay? You should try them all. So you have multiple techniques and combine this with the learning rate. Okay, let's say you want to try 10 different learning rates with 6 optimizers. Okay, 60 combinations multiplied by 2 or 3 initialization techniques. Okay, that's about 200 problems, 200 trainings to run. And, well, maybe your algo has other parameters too, right? So pretty quickly, the combinations become pretty bad. So there are techniques to do that. People do grid exploration, etc. So they build that, let's say, 3D matrix with learning rate and optimizer and maybe initialization, and they pick 200 random set of values in there, and they train 200 models with those parameters, and they see which one is best. That's what people do, right? So that's what I'm saying. If you think you've trained one model and your job is done, maybe you were extremely lucky, right? Or maybe you need to keep training, right? So probably something we need to fix for you guys. Okay, a few more things. So you can reduce model size. So there are 2 techniques. So all the weights, they're 32-bit floats. There's a technique called mixed precision training where you actually truncate them to 60-bit floats during training. So you end up having a model that's twice smaller. So for cloud-based architectures, it doesn't really mean anything, but for my Raspberry Pi, the difference between 200 megs and 100 megs, that's worthwhile, right? So for IoT applications, that's interesting. And there's even a project that does binary weights, right? So it's not even floats, it's -1 or +1 values, okay? And obviously they get to crazy small models, as you can see here. Right? The same model is shrinked from 44 megs to 1.5 meg. So that would really fit anywhere. And they only lose 4% accuracy. So that's a lot, right? It's a lot, 4%. But it's the difference between not being able to do deep learning on that device, right? Imagine it's the tiniest thing. It could be a fire detector or something, right? Fire detectors, they're not going to have 64 megs of memory. No way. Too expensive. Maybe they can have 2 megs, right? So it's the difference between no deep learning at all or slightly degraded deep learning. So this technique, it's really opening up deep learning to very, very constrained devices. So if you're interested, if you work in IoT, you should look at this. Okay, you can monitor the training process. You saw that in my logs. You do this by creating a callback saying, every time you've run 10 batches, just display the accuracy. right? So batch 10, batch 20, etc. Okay, just to get some logs. And don't forget to save parameters after each epoch, right? You're going to train for 200 epochs. Okay, and maybe, okay, you could say, well, then I'm going to use the model that I get after 200 epochs, right? That's got to be the best one, right? Because I trained longer, so it's better, right? Not always. Because something like this could happen, right? So training accuracy goes up. You saw this in my examples. And you will get to 100%. If you saw that synthetic dataset example this morning, you will be able to learn anything perfectly, given enough time and a large enough network. Okay, the loss function, so the difference between the prediction and the actual truth will go to 0, right? But maybe you'll see something like this in validation accuracy. It starts to drop after a point. So you definitely don't want to use this model, epoch, whatever. You want to use that one. So how do you know if you didn't save the models after each epoch? Right? So you want to save the models after each epoch, and then looking at your training graph, you could say, here's the best one. You could plot the validation accuracy and say, well, actually, epoch 1, 2, 3 was the best, not 200. Okay? And what happens here is called overfitting. It's you learn your training set so well that it's the only thing you know, basically, and you're not able to generalize to data that you haven't seen. Okay, that's a really, really bad problem. Okay, and we saw it with this synthetic example this morning. We're able to learn crap perfectly, but when we look at real samples, it's meaningless, right? Overfitting. So very bad problem. So, as a conclusion, so there's a lot of literature on that stuff. Just Google, what learning rate should I pick, right? And well, you get weeks of reading. So good, read some stuff, but the truth will come out of your own experiments. Okay, because what worked for that guy in that university is a different problem than yours, right? Different data set, maybe different network, different parameters. So there is no absolute truth, right? That's the only thing I know. And you have to try with your own data and your own network. So there are some guidelines, not too small, not too big, no. But okay, run your examples and train 1,000 models and pick the best one. Right? If there's a single truth to deep learning, that's probably it. Okay, which leads me to, you need to have the right infrastructure to do it, okay? And maybe it's not 1,000, maybe it's 100, right? But I'm French, I'm exaggerating. I cannot help it. Train a lot of different models with a lot of different values and pick the best one. Actually, pick the best ones, because there's a good technical ensemble learning where people, let's say, train a lot of models and they pick the 5 best ones and they run prediction for the 5 and they average it, okay? The idea here is each network is going to make silly mistakes on some samples, absolutely silly mistakes. So if you average it, then, okay, the other networks won't make the same mistakes, so they will look a little less bad, right? And if you see all the competitions for image recognition, etc., all the winners now, they use ensemble learning, ensemble techniques for prediction, ensemble prediction. So anyway, you need to make sure your infrastructure runs very well, because you're going to train a lot, okay? Compute, storage, everything that we saw, that's all important, right? Don't lose sleep over that, but if something's not working, you should see it and fix it, because it can literally multiply training times by 2 or 3 if they don't run right, okay? It happened to me. Spot instances to optimize prices. And it's really missing a line, say, or you could use SageMaker, right? And now you understand this predates the SageMaker release. So it's not a clever marketing speech on my behalf, because I can't really do that anyway. But as you can see, SageMaker is actually solving a lot of these problems. And it's the reason why SageMaker was built, is to help customers, not worry so much about these. Not all of these go away, but a lot of these go away with SageMaker. Okay. Still, I fully recognize SageMaker is not the right tool for some tasks. I would love to hear about that. Okay, so if you are running, not today necessarily, later on, if you are running SageMaker, if you are running deep learning or machine learning tasks on your own infrastructure or on EC2 instances, and you tried SageMaker and you didn't like it, or it didn't work right for you, I would love to hear about that. I love it when people say it's great. I love it even more when they say, man, it sucks. Or we would like to love it, but this and this and this are, making us hate it. So if you have negative feedback on SageMaker, please ping me on Twitter or LinkedIn and send it to me, right? You might even win some AWS goodies, who knows, all right? No promises. Okay, so, well, I hope this is useful. I know it's a lot of different techniques, but, you really need to worry about all of this as well. So, some resources, and that's tiny, but, so again, the Amazon blog, the MXNet code base and websites, and some blog posts that I wrote on specifically on those problems, how to use an NPAC in MXNet, how to do that tuning process on the Python, on record.io, etc., with C5 instances, etc., etc. So these are really, more of the same, but with details and code and stuff that you can actually reuse. Okay, so just gave you the overview, but if you want to zoom in, please go there and take a look. Okay, so let me take a final look at that classification notebook. I'm so sorry it's taking that long. Oh, yeah. Okay. So if you were not there, you're wondering what the hell I'm doing. Okay, this is one of the examples I couldn't complete in time in the previous session. So here I'm using SageMaker with the built-in image classification algorithm. And I took a pre-trained image classification network. I fine-tuned it on my data set, and now I want to do predictions, right? So I've got some images that correspond to the classes that I have in the data set. All right, so I guess that's a dog, which is good because I have dogs in the data set that I learned. Okay, so now let's run that image through the model, and yeah, 92% says it's a dog. So that worked. Okay, and keep in mind, I only trained for 10 epochs. So the training job was actually, I'm trying to look at how long it took. I don't have the time. But yeah, maybe 10 minutes or something. Do I have the training log? Where is it? No, I don't have it here. Okay, it's in CloudWatch logs. But I just trained for, just a few minutes. So I didn't train from scratch. So let's try the bird, maybe. Okay, so that's a bird. What does my model say? 56%, okay. It's still a bird, right? And the other choice would be this class. I don't know what that is. But yeah, okay, it's still a bird, so 2 for 2. Let's try the horse. Ah, this one's wrong. No, it's not a deer, right? All right. So 2 out of 3. But you only see the head of the horse. So maybe the data set has really, full horse pictures. Who knows? And should we try the truck? Okay. Crossing my fingers here. Yeah, okay, no doubt that's a truck, right? So, as you can see, that's a really cool technique, right? I've been talking about fine-tuning for a while, over and over today, and this is a really simple technique, right? So, if you want to contrast this to how would you do this manually, well, you would create an EC2 instance with the deep learning AMI. You would upload your data set to the instance, probably. You would need to pick. You would need to write an MXNet or TensorFlow script, downloading a pre-trained network from wherever, right? Loading the data sets, launching a training process, etc., etc. So you can definitely do it. I've got other demos that do that, right? So you could do it without SageMaker. But with SageMaker, the only thing that you do, right? Sorry for those of you who have seen this before, and I'll close on that, right? You pick the Docker image in your region that implements that image classification algo. You download the data set to SageMaker, and use that record IO file I was talking about, right? Just one file for the training set and one file for the validation set. You define some training parameters, how many epochs, how many classes, etc., the learning rate. You put that stuff in a JSON document, right? This is really the same thing in JSON form. You say where the training set is, where the validation set is, and you fire up the training job, right? And you say, well, I want an M4 instance. Where did I say that? Here. Oh, no, it's running on a P2 instance here. One instance. Done. So you wait for a few minutes. And then you do the same thing to deploy the model, create a configuration, M4, deploy, etc. Okay, so that's a different way. So if SageMaker is enough for you, please use SageMaker. You're going to save a whole lot of trouble managing all the stuff I actually talked about in this last talk. If SageMaker is not enough, please tell me why, get in touch. And use TensorFlow, MXNet, your favorite deep learning library on the deep learning AMI, and using all the techniques that I described, you should be able to get good infrastructure performance and good model performance. But as you can see, it's a bit of work. So SageMaker will be your friend here. Yes?
Where in the code do you state that you're training the network to take courses?
So I'm actually not. It's in the data set. So here, where's that data set? Here. Where does it come from? All the way up. Okay, here. What this record IO file is my 50,000 training images organized in classes. Okay, so the way it usually looks is I've got one directory per class, so all horses, etc., and the model knows nothing about horses or trucks, right? It knows about class 0, class 1, class 2, class 3. That's it. Okay, and it's just me at the end saying, okay, class 2 is a horse, and I'm printing a horse. But it's all about numbers, right? There is no domain knowledge in here at all. Okay. Yes.
We talk a lot about techniques here.
Yes.
There's also the other part about estimating projects, and you have actual time contractors, I have
Sure.
clients on the other end. And my experience with these things are that even though you do like one set of data and you can come up with all these numbers and iterations and learning rates, it doesn't transcribe over to not anything other like that. So pretty much every time I have to do something with almost the same kind of input data, I have to go through all of these processes over and over again. At one point, I failed. Probably used the wrong network type. And in the end, I still get things from a result perspective. I know things almost. I mean, I can still fail, like you just did here with the horse.
Yeah.
And then you have a client on the other side. Most of the time today, I mean, I do understand that this is not a perfect system. But many clients doesn't understand that. So when you try to estimate projects and then come back and say, you know what, I'm done. And they say, but you're not recognizing everything 100%.
Yeah.
So, and my question to you is, have you failed?
Every single day.
Able to do
Every single day, yeah, every single day. There's one specific algo in SageMaker, I'm not going to name it. I still haven't gotten it to work correctly, and well, it's my fault. But
It's a tricky situation.
it is a tricky situation because usually, it's hard to say always in this case, but usually it's all about the data set, right? The typical problems that you will have is that if you look at the training set here, training sets, and that's very tiny, I'm sorry, but these are really tiny images. Training sets tend to be very nice, right? So if you look at this one here, I don't know, if you look at the deers, even with very tiny images here, it's clear it's a deer, right? So there's one single thing in the picture, right? This one doesn't even have a background. Okay, you see the antlers very clearly. So these are deep learning friendly pictures, you know? And that's the training set, and the validation data set is the same thing, because the validation data set is a part of this. So look at the ship pictures. I mean, they're really nice ship pictures. There is no doubt this is a ship, right? But real life pictures, they're never like that. Okay, maybe the subject is not centered in the picture, or maybe there's other stuff in the background. Yeah, maybe there's a dog, and maybe there's a person next to the dog, right? So even though that data set doesn't know anything about persons, you know, it's noise. It could confuse. I don't want to say people look like dogs, but maybe some do. But you know what I mean. Those training pictures, they look very nice, and they probably don't look like what end users will upload and use. If you think at pictures that people take with their mobile phones, none of them is really going to look like that. They're going to be fuzzy and overexposed, and there would be all sorts of objects around the subject, etc., etc. So that's actually something I didn't talk about because it's really data set management. But it's important that you inject in your training set pictures that will really, or in the validation set, pictures that will really, really look like what real life samples will look like. Because if you have a very nice data set like this, yeah, you can learn it pretty well. And then people say, okay, now we've got real life pictures, and you push them through that, and they don't work because they're too different. So the distribution of the training set should be similar, or close, maybe not similar, but should include the training set. The training set should include some low quality real life pictures, because your network needs to learn how to recognize them. And actually, data augmentation is a good, if you don't have those samples, data augmentation is a good way to do that, because data augmentation is going to distort the pictures. It's going to, change the colors. It's going to flip them. It's going to stretch them, crop them, etc. So some of the augmented pictures, they look like crap, right? But that's actually good, because if you say, well, let's say I take this, this dog here, and I'm cropping the picture like this, so maybe I can see only one eye, half of the dog's face, and maybe, I tweak the color and the dog becomes, slightly greenish or something. Okay, if you show that to a kid or a person, they will still say it's a dog. So the network should be able to face those adversarial samples and say, yeah, okay, it's low quality. Maybe the probability that will be output will be lower, but I will still classify this as a dog. So it's really, that's a difficult issue. So if you have real life samples, throw some of them into the training set, right? Not just very clean and nice samples like this. And that's going to help a lot. But you will never be done. There will be mistakes. So the thing is, if you go to your customer and say, my network is 99% accurate, right? If I was the customer, I'd say, okay, show me the validation set. Because if the validation set is looking like this, I'm going to say, okay, no. I want 99% on a crappy validation set. So go and build a crappy set, learn it 99% right, and then okay, we're done.
I mean, the clients today don't have the skill to be able to require that. You know what I mean?
Yeah, but then they shouldn't use that technology. They should use Amazon recognition.
Of course, but if you're asking like any retail store,
Yeah.
they're going to want an ML anyway. So.
Yeah. So yeah, it's a good point. So if they're not sophisticated enough to understand what kind of work is required from them, which is, okay, show me your data set. What kind of samples would you like me to predict, right? What's the business problem? Oh, I want to classify images that my users upload via the mobile app. Okay, can I get 1,000 of those? No. Okay, well, okay, so I'm going to pretend I have 1,000 of those by building crappy-looking samples using data augmentations, and maybe we can start from there. But you need to be very nasty to the training set, right? That's the robustness issue comes a lot from that. Yeah, you should be able to demonstrate that you score high on these kind of pictures, right?
I think prototyping is really important.
Oh yeah, it's iterative, iterative as hell. That's why I'm saying train 100 networks, train all the time, try different data augmentation, just, yeah. Try to make the network as robust as possible to ugly samples. And like my ugly 9, right? So it's the ugly 9 syndrome. Yeah, you need to have you need to score high on those crappy looking pictures. If you do that, then probably your network is doing a good job. Yeah.
But if you have many different objects, will the accuracy decrease?
So if we had a deer and a dog in the same picture, your guess is as good as mine, right?
More automobile, let's say helicopters and
So again, it depends. Maybe the helicopter is gonna be. Don't we have airplanes in that one? Yeah, I think we do. No, maybe it's class 1. Yeah, okay. So if we have other objects that kind of look like that, it might trip the network. Let's say if we have a bear, some dogs, some big dogs, they have a similar shape and color to a bear. So so that's why I'm saying it depends. Okay, so obviously, okay, that's not a bear, but that big dog here, you never know. So there will be some mismatch. I mean, there's a famous example of, did you see that, the muffin and the chihuahua? Yeah? It's very cool. You take a blueberry muffin picture with the blueberries kind of looking like the dog's eyes and the nose, and you try that with deep learning networks, and it says it's a chihuahua, and the other way around. And you take an ugly chihuahua, and it says it's a blueberry muffin. Because at the end of the day, it's all about geometric shapes. So sure, those networks, they get better all the time, but they will still make mistakes. So that's why you need very large data sets, lots of samples per class, data augmentation, etc., etc.
I mean, what I meant, if you just train the algorithm network to recognize airplanes, will it be better?
Absolutely, very good point. The more classes you have, the harder it gets, because it's an easy task to say, is this an airplane or something else? Versus, is this an airplane or a truck? Right? So, sure. So it's like the hot dog, not hot dog, silly thing, right? So saying, is this one thing or not, is easy. That's an easy task. So if your business problem is, I'm only interested in detecting trucks, right? Maybe it's a toll or something, I don't know, right? So you don't care if it's a car, you don't care if it's a motorcycle, you don't care if it's anything, or a moose on the highway, right? You don't care. You want to know if it's a truck. So you could say, well, I got 2 classes. Class 0 is trucks, class 1 is everything else. And you would dump, all the other images in anything else. And you will learn that very well, very, very well, right? Of course, the more classes you get into, some horses can be confused for deers, as you can see, and probably some dogs could be confused as cats, and because some of them are kind of similar, right? So, all right. Well, thank you very much for sticking around. I hope you learned a lot. And if you so you will get the slides. You should receive an email in the next few days with the link. If you don't, well, just either connect on LinkedIn and ask me for the link. Julien Simon AWS, there's only one. And or ping me on Twitter and just ask me for the link. Okay, happy to help. And if you have questions later on, just get in touch. That's what I do as well. I just don't only stand and give silly examples and silly talks. I also actually help people when they need me. Right? All right. Thank you very much, and I hope you had a good day with us. I sure had a good day. Thank you very much.